Alright, we're going to take a look at some example problems for motion in one dimension. You're going to want to have your equation sheet out in front of you, and it's going to be a lot about determining which equation will work best with the givens and the unknowns that you have available. So I'm going to try to bring this in as close as possible so that you can see what I'm doing. Alright, so we're going to start with number 14. Number 14 asks us, if a car is traveling eastward, can its acceleration be westward? Explain your answer and use an example in your explanation. So this is number 14. So the answer is yes. If you step on the brake, then your car is accelerating in the opposite direction. So I guess instead of giving an example, I kind of put an example in my answer. If you're in a car and you're traveling forward and you throw your foot on the brake, what you're actually doing is you're causing your car to then be accelerating in the opposite direction. So, yeah, you might be moving forward still, but the acceleration is negative. Okay. So think about that one. It's kind of strange. Number 19, we have a car that accelerates uniformly from rest, that's a big key thing there, that word, rest, to a speed of 65 kilometers per hour, which I gave you in the problem is 18 meters per second, in 12 seconds. Find the distance the car travels during this time. So for number 19, let's use the guess method. So for our givens, I have V naught equals 0 kilometers per hour, which is also 0 meters per second. How do I know that's the initial velocity? Well, the car started at rest. And then it travels to a speed of 18 meters per second. And that entire time took 12 seconds. And those are our givens. Okay, so what are our unknowns? Well, I need to figure out how far did that car travel. So I'm looking for my position. I don't know what my displacement is at the end there, our change in x essentially. Okay, so I'm going to look and see what equation has initial velocity, final velocity, that's what this velocity is, and time where I can find the change in x. So if I look, I can find an equation that has the change in x equals v naught plus v divided by 2 times t. So since this is one time interval, we can use this specific equation. So then I'm going to take my numbers and plug them in. So change in x equals 0 meters per second plus 18 meters per second divided by 2 to give me the average velocity of that trip times our 12 seconds that it took to get up to 18 meters per second. So when I multiply all of that through and divide, what I end up getting is my change in x equals 108 meters. Put a box around the answer, and then you are good to go for number 19. Let's look at, let's look at number 22. For number 22, I have a car that starts from rest and travels for 5 seconds with a uniform acceleration of plus 1.5 meters per second squared. Then the driver applies the brakes, causing a uniform acceleration of -2 meters per second squared. If the brakes are applied for 3 seconds, how fast is the car going at the end of the braking period, and how far has it gone from the start? Okay, so let's start with our givens. We have V naught equals 0 meters per second, T naught equals 5 seconds. Our initial acceleration is plus 1.5 meters per second squared. Our final acceleration is -2.0 meters per second squared. And the time that the brakes were applied and we were traveling at this negative acceleration was for 3 seconds. So it's all about evaluating what's going on in that problem. Okay, so then what are our unknowns? Well, let's see, I see that's a little blurry, let's fix that. There we go, sorry about that. Let's see, so for our unknowns, we have, I can't think straight, let's just turn that off.